Welcome back. If you have a gas barbecue grill at home, you may or may not know the gas in the tank is propane. Let's say you're a chemical engineer working for the propane company and you need to calculate how many moles or how many grams of propane are required to fill the tank. In order to do that, you need to combine the molar mass concept we learned in the last lesson with the basic strategy of setting up calculations we've used throughout the course. In doing so, we'll be able to again address the fundamental question a chemist frequently needs to answer. That is, how much or how many? Let's start with a review of the molar mass concept. Calculate the molar mass of propane, C3H8. Stop the video now. If we add the total mass of each element, we get the molar mass of propane. Recall the units are grams per mole. Since molar mass is essentially a fraction in which the quantity in the numerator, 44.09 in this case, is equivalent to the quantity in the denominator, 1 mole, we can use molar mass as a conversion factor to help us convert between grams and moles. For example, the molar mass of propane that we just calculated can be made into this conversion factor or this one. Which one we use all depends on whether we're converting from moles to grams or grams to moles. Remember, if you bring the unit grams to the bottom, you also need to bring the number to the bottom, the 44.09 in this case. You can make similar conversion factors using the molar mass of any substance, as you see here for zinc, water, and barium phosphate. Okay, so you're that chemical engineer. And let's say your task is to determine how many grams of propane constitute 0.750 moles of propane. Let's go through it one step at a time. Like most calculations we'll do this year, first write down the final unit you'll need to solve for, which in this case is grams of propane. Don't just put grams, you need to specify grams of what. Second, write down your given quantity. Then start setting up a conversion factor. And now predict what unit, no numbers yet, just units, goes in the denominator. Stop the video for a moment and write it in. We need moles of C3H8 in the bottom to cancel the moles of C3H8 that we started with. Next, stop the video for a moment again and add the unit, no numbers, just the unit that you think goes in the numerator. Let's try grams of C3H8 since that's what we're solving for. Now grams of C3H8 is okay only if we know how many grams are in a mole of propane. Well, we do. That's the molar mass we calculated a couple minutes ago. It's 44.09 and we put it by the grams. Since the only unit that doesn't cancel is the one we want, we simply do the arithmetic and get our answer. Okay, here's another one. Please try this entire one on your own. Stop the video now. Well, we set this up similar to the previous one, giving us 106 grams of zinc. The 65.38 you see here is the atomic mass of zinc from the periodic table. Don't forget to ask in class if you have any questions. Your next one is similar. Stop the video now and give it a shot. Okay, the unit setup is the same as the others, but since this problem deals with sodium chloride, we need to calculate the molar mass of sodium chloride. You get that, of course, by taking into account the atomic mass of sodium and adding it to the atomic mass of chlorine. Let's now try another assisted problem. Notice a key difference with this one. This time we're going from a known quantity of grams and we need to find moles, not the other way around. First, let's write down where we're headed. Mole of lead 2 sulfate. Now, write down what you're given and begin setup of your conversion factor. Now, unlike the previous 3 problems, what unit needs to go in the denominator this time? Stop the video and write it in. This time, grams goes in the denominator because we need to cancel the grams we started with. Stop the video again and predict what unit goes in the numerator. Now we need moles in the numerator because that's the unit we want in the end. Okay, please first calculate and then add the value for the molar mass of lead-2 sulfate to the conversion factor in the proper location. Stop the video. Notice how we put the value for molar mass in the denominator. The molar mass value always goes where the gram unit is. If grams is in the denominator, you need to bring the molar mass downstairs too. Now, please do the arithmetic and solve the problem. Stop the video now. The math this time is 18.55 divided by 303.3 to give us approximately 0.06 moles of lead-2 sulfate. Please try this next one on your own. Notice the mass is in kilograms to begin with. Stop the video now. Hopefully you remembered to first convert kilograms to grams before using the molar mass conversion. Ask in class if you have any questions on this solution. Now that we've practiced the gram to mole and mole to gram conversion several times, let's combine these types of calculations with the ones we did in the mole calculations part 1 lesson. Recall in those calculations, instead of dealing with mass, we dealt with how many particles, how many atoms, how many molecules, how many ions. In those calculations, we needed to employ Avogadro's number, 6.02 times 10 to the 23rd. Let's start with a brief review of conversion factors involving Avogadro's number. Complete the following table, please. The first row is done for you. Stop the video now. For water, 1 mole contains 6.02 times 10 to the 23rd molecules of water. Or we could write the inverse. Notice we didn't say atoms of water, as in the sodium row above, because the fundamental unit of water is a molecule, a group of atoms, 2 hydrogens and 1 oxygen, tightly bound to make a discrete particle called a molecule. We see similar conversion factors for lithium nitrate, with the only difference being the fundamental unit of an ionic compound, such as lithium nitrate, is referred to as a formula unit, not a molecule. Now that we've reviewed how to make a conversion factor using Avogadro's number, 6.02 times 10 to the 23rd, let's practice calculations where you use both the types of conversion factors you see on the screen now with the molar mass conversion factor, the one that is grams per mole. In this first one, I'll get you started. As usual, start by indicating what we want to solve for. Then write down what we're given. Then begin the setup of your conversion factor. Now we put grams of zinc in the denominator because we know we want to cancel that. Don't put any numbers yet. Numbers don't make sense if you don't have a unit in the denominator and the numerator. Now the question is, what goes in the numerator? Well, we see that we want to end up with atoms of zinc. So we might think to put atoms of zinc here. The problem with that is we don't know how many grams of zinc are in an atom of zinc, or how many atoms of zinc are in a gram of zinc. That's not one of our common conversions. But we do know another unit that can go in the numerator that often does go along with grams in the denominator. Stop the video and write down what you think that unit is. It's moles of zinc. This works great because we do know how many grams of zinc are in a mole of zinc. It's 65.38, the molar mass from the periodic table. Now, we need one more conversion factor and then we can solve it. Try to figure out what that conversion factor is and then solve the problem. Stop the video now. We use the conversion factor dealing with Avogadro's number. Moles cancel and we're left with atoms of zinc. Make sure to ask in class if you don't understand this result. Okay, hang in there. Just 2 more calculations. Try this next one on your own. Stop the video now. Here you see the solution. Make sure to ask in class if you're unsure where any of these numbers come from. Okay, last calculation. Please try this entire problem on your own. Stop the video now. In the solution here, note that Avogadro's number needs to be in the denominator because there are that many atoms in 1 mole, not that many moles in 1 atom. Okay, last question. Let's say a student performing one of these calculations finds her answer is 8.76 times 10 to the 24th grams of sodium chloride. She takes a look at that answer and immediately thinks to herself, that looks odd. Comment on her perception. Is she correct in thinking the answer is strange, and why? Stop the video now. Absolutely, she is correct. Notice that she has solved for a mass in grams. Grams is a macroscopic quantity generally. 300 to 400 grams, for example, is the typical size of a cereal box. 8.76 times 10 to the 24th grams, on the other hand, would be about 2.50 times 10 to the 22nd cereal boxes. That's almost 1 mole of cereal boxes. I don't know exactly how much space that would take up, but let's just say it would easily cover the entire planet and make a fairly high stack at the same time. The point here is, whenever using Avogadro's number, ask yourself if the answer makes sense. The only time you'll have an answer that is around the order of magnitude of Avogadro's number, like 10 to the 23rd or 10 to the 24th or even 10 to the 20th, is when you're solving for how many of very small particles. For example, how many ions or how many atoms or how many molecules. Well, I know this was a tough one, but thanks for listening and see you next time.